Okay, let us continue the third part of the class. Okay, we have taught to here. Okay, therefore, when d is small, 2 pi HTHR over lambda d is approximately pi over 2. Okay, where does this equation come from? Okay, let us go back to the previous page. Okay, the transition between these two regions, okay, that is, the first region is 1 over 2 square. That is, the received power decreases as 1 over 2 square. And the second region, that is at large d, PR decreases as 1 over d to the power of 4. Occurs when the argument in the sine term. Okay, what is the argument in the sine term? Okay, that is, okay, in equation 4.6, the argument in the sine term is 2 pi HTHR over lambda d. Okay, becomes smaller than about pi over 2. Okay, so 2 pi HTHR over lambda d is approximately pi over 2. Okay, so PR is approximately 4 pt GTGR times the square of lambda over 4 pi d times sine square of pi over 2. Okay, because the argument in the sine term now is approximated to pi over 2. And we know that sine of pi over 2 is equal to 1. Okay, so we can cancel this term. And this equation is equal to 4 pt GTGR times lambda over 4 pi d square. Okay, so we can see that in the denominator there is a term d square. So this equation is proportional to 1 over d square. Okay, when d is large, this term 2 pi HTHR over lambda d is small. Okay, because d is in the denominator. The series expansion of sine x at x being equal to 0 is, okay, sine x is equal to x minus x to the power of 3 over 6 plus x to the power of 5 over 120 plus big O of x to the power of 7. Okay, it is the Taylor series, okay, which you have learned in the course calculus. Okay, and what is the big O notation mean? Okay, it means that it contains all the terms, okay, which is contains x to the power of 7 and x to the power of 8 and x to the power of 9, etc. Okay, all the higher order terms. The order is higher than or equal to 7, which are all contained in this big O of x to the power of 7. Okay, because now x is approach 0. Okay, so it means that x is very small, and x to the power of 3 is much more smaller. Okay, much more small. Much smaller. So we can neglect it. Okay, so similarly, we can also neglect the x to the power of 5 term and big O of x to the power of 7. Okay, so sine x is approximately x. Okay, so PR is approximately 4 times PT GT GR times lambda over 4 pi d squared times 2 pi HTHR over lambda d squared. Okay, because originally it is sine squared 2 pi HTHR over lambda d. Now, because sine x is approximately x, okay, so we use x squared instead. Okay, so we can see that here is a d squared term in the denominator, and here is also a d squared term in the denominator. So this equation excuse me, is proportional to 1 over d to the power of 4. Okay, so so it completes the solution to this problem. Okay, let us go back to the slides. The position of this equation number is wrong, in the wrong place. Okay, good. The distance at which this occurs is often referred to as the breakpoint distance, which is denoted by dB. Okay, what occurs? That is the transition between these two regions. Okay, this region and this region. Okay, it follows that dB is equal to 4 HTHR over lambda. Okay, let me fix the position of the equation number. Okay, how do we derive this equation? Please see the handout. Okay, page 33. Excuse me. Problem 1. Derive equation 4.7. Okay. Solution from page 32 of the slides. We know that the transition between the two regions, the 1 over d squared and 1 over d to the power of 4 regions, occurs when the argument in the sine term becomes smaller than about pi over 2. Therefore, referring to equation 4.6, okay, let us see equation 4.6. Okay, is this equation, and the argument in the sine term is 2 pi HTHR over lambda d. Okay, so we can write down the following equation. Okay, 2 pi HTHR over lambda dB is equal to pi over 2. Okay, after some simple calculation, one can find dB is equal to 4 HTHR over lambda. Okay, because here is a pi, we can cancel these two pi's, and we move dB to the right hand side of the equation, and move the 2 to the left hand side of the equation. Okay, and reverse the side of this equation. Then we have dB is equal to 4 HTHR over lambda. Okay, let us go back to the slides. Okay, figure 4.4 shows the comparison between the two-ray model predictions and the measured data collected by the author of the textbook. Okay, let us see figure 4.4. Excuse me. Okay, figure 4.4 is the comparison between two-ray predictions and the measured path loss at 450 MHz. Okay, the x-axis is the distance in meters. Okay, you can see that the distance is plotted in dB, and the y-axis is the attenuation from negative 100 dB to negative 20 dB. Okay, and the bold black line is the theory. Okay, this line. Okay, and the dotted line is the measured. Okay, measured data. Okay, this line. Okay, like this. Okay, the measured data in this plot were collected by measuring the propagation loss between a fixed transmitter and a mobile receiver van in a flat open field at 450 MHz. Okay, what is van? Let us see the handout. Okay, page 34, problem 1. What is van? Solution. A medium-sized road vehicle used especially for carrying goods that often has no windows in the sides at the back. Okay. Let us go back to the slides. Okay. Okay, it shows measured attenuation as a function of distance between 2 points. The two-ray predictions are shown superimposed. Okay, what is superimposed? Let us go to handouts. Okay. Okay, page 36. Problem 1. What is superimposed? Excuse me. Solution. To put especially a picture, words, etc. on top of something else, especially another picture, words, etc. so that what is in the lower position can still be seen, heard, etc. Okay, so we can see that the two-ray predictions Okay, so we can see that the two-ray predictions are shown superimposed. Okay, here on the measured data, and denoted by theory in the legend. Okay, the theory in the legend. In the measurements, the heights of the transmitter and the receiver were 2.3 and 2 meters, respectively. Okay, it follows from equation 4.7 that the breakpoint, it should be breakpoint distance, is equal to 27.6 meters at 450 megahertz. Okay, how do we get this value? Or is this value correct? Okay, we need to check this. Okay, so we can use the MATLAB to write Okay, let me clear the command window first. Okay, we can use the MATLAB to write a simple computer program like this. Okay, ht. Okay, this is the height of the transmitter. Okay, it is important to write comments in a program, a computer program, and the unit is meters. Okay, ht is equal to 2.3 meters. And this is the height of the receiver. Okay, and HR is equal to 2 meters. Okay, and C is equal to, it is the speed of the light. Okay, GHT. Okay, the unit is meters per second. Okay, C is equal to 3 times 10 to the power of 8 meters per second. Excuse me. And this is the frequency. Okay, frequency. Okay, in hertz. Okay. So F is equal to 450 megahertz. So which is equal to 450 times 10 to the power of 6 hertz. Okay, and the lambda is the wavelength. Okay, in meters. So we know that wavelength is equal to the speed of the light divided by frequency. Okay, so lambda is equal to C over F in meters. Okay, so finally we will find the breakpoint distance. Okay, dB. Okay, it is also in meters. Okay, dB is equal to 4 times ht times hr over lambda. Okay, so we can click the run button. Okay, then we will get the answer. Okay, dB is equal to 27.6 meters. Okay, let us go back to the slides. Okay, so this value is correct. We have just checked it. Examination of this plot confirms that the slope of the measured data changes at a distance approximately equal to that value. Okay, let us see 27.6 meters. Okay, in figure 4.4, it is 10 meters and 20 meters and 30 meters. So 27.6 meters should be in this interval. Okay, it is approximately located here. Okay, so we can draw a vertical line. Okay, and okay, sorry. Okay, please wait me. Okay, good. Okay, and intersect with the measured data. Okay, so you can see that at this point, okay, before and after this point, the slope of this curve changes. Okay. Okay, free space and two-ray propagation are, of course, only two of many possible power law models that are found to model propagation environments. In these two models, path loss increases as the square of the distance. That is, it is the free space propagation model, or as the distance to the fourth power. Okay, so for the two-ray propagation model, okay, when the distance is smaller than the breakpoint distance, the path loss increases as the square of the distance. And when the distance is larger than the breakpoint distance, okay, the path loss increases as the distance to the fourth power. Okay, in general, large-scale path loss, okay, please note that path loss is a part of the large-scale fading. While not necessarily obeying square law or fourth law behavior, is observed to increase as d to the power of n, where the exponent n can be any positive real value. Okay, table 4.1 lists empirically determined values of n for various environments. Okay, let us go to table 4.1. Okay, table 4.1 lists typical path loss exponents for various propagation environments. Okay, when the environment is free space, the exponent is 2. Okay, we have already known it. Okay, when the environment is urban area cellular, okay, the exponent is 2.7 to 3.5. Okay, this is the reference. Okay, 61. Okay, let us see reference 61. Okay, reference 61 is a book written by Theodore S. Rappaport. Okay, he is a professor in the New York University. Okay, and his recent research includes the 5G channel model measurement. Okay, and the title of the book is Wireless Communications Principles and Practice, second edition, Prentice Hall, published in 2002. Okay, when I was a PhD student, I took a course, Wireless Communications, and the professor used this book as the textbook. Okay, so let us go back. Okay, go back. Okay, good. Okay, and when the environment is line of sight urban, the exponent is 2 to 4. Okay, please see reference 39. Okay, let us see reference 39. Okay, reference 39 is a paper written by J.R. Hampton. Okay, J.R. Hampton is the author of the textbook. And N.M. Merhib, W.L. Lane et al. And the title of the paper is Urban Propagation Measurements for Ground-Based Communication in the Military UHF Band. Okay, where UHF means the ultra high frequency. Okay, this paper is published in IEEE Transactions on Antennas and Propagation in 2006. Okay, let us go back. Okay, when the environment is non-line of sight urban, the exponent is 5 to 20. Okay, also please see reference 39. Okay, when the environment is indoor line of sight, the exponent is equal to 1.6 to 1.8. Okay, please also see reference 61, table 4.2. Okay, when the environment is indoor obstructed, the exponent is equal to 4 to 6. Okay, Okay, please also refer to the reference 61, table 4.2. Okay, it is 25 minutes. See you next time. Goodbye.